In a typical T&D system, two basic types of high-voltage cables can be used to route power to customers. The main difference between the cables is the insulation that isolates each cable's conductor. This is a solid dielectric cable. It uses a pre-molded material with a high insulating property. The material is applied evenly in a solid mass over the cable's conductor and conductor shield. Two of the most commonly used solid dielectric cables are cross-linked polyethylene, or XLP, and ethyl propylene rubber, or EPR. Paper-insulated lead-covered cable, or PILC cable, uses a different type of insulation. This insulation is composed of layers of paper which wrap around the conductor and the conductor shield. A lead cover protects the insulation. The number of layers and the thickness of the paper insulation are in proportion to the operating voltage that will be applied to the conductor. The paper that is used for the insulation is saturated with an insulating oil. The oil in this process makes the paper layer a more efficient insulator. Earlier in your training, you watched as solid dielectric cables in T&D systems were spliced for repairs and to extend their length. You've also seen some of the more common ways to splice a solid dielectric cable. This program will focus on the methods involved in splicing paper-insulated cables and splicing a PILC cable to a solid dielectric cable. Let's begin this part of the program by taking a look at how PILC cable is designed. This is a 15 kV insulated single conductor paper lead cable. It's similar in design to a solid dielectric cable. There is a conductor in the center, which is generally made of copper. The copper conductor is stranded to allow greater cable flexibility. Over the conductor is a layer of semiconductive material. This layer is the conductor shield layer, which rounds out the conductor, reducing the voltage stress on the cable's insulation. This layer also makes it easier to build the cable without any voids or air spaces between the conductor and insulation layer. Air spaces could ultimately lead to premature failure of the cable. The most important part of the cable is the cable's insulation layer. Unless the insulation maintains its integrity, it will not keep the voltage isolated on the conductor. The number of layers of paper the insulation will have depends on the voltage that the cable is designed to handle. The higher the voltage, the more layers and greater thickness the insulation will have. Other layers of the cable support the cable's insulation, either mechanically or electrically. An insulation shield rests over the paper insulation layer. You learned earlier in your training that this layer is electrically grounded and semiconductive. It serves the cable's insulation by putting a uniform grounded layer around the insulation, evening out the voltage stress in the insulation. The insulation shield on the cable in this example is a semiconductive tape. Over the cable's insulation shield is the lead cover. This layer serves the cable in two ways. One is to supply the insulation shield with a way to get rid of any static charge that may build up. Since lead is a conductor, if it's grounded, it can be used like the metallic insulation shield of a solid dielectric cable. The lead cover also serves the cable by mechanically sealing the underlayers of the cable from the environment. This is very important to a paper-insulated cable, since oil-impregnated paper is not very resistant to water or corrosives that are found in underground conduits and manholes. Protecting this seal during cable installation and re-establishing the lead cover during cable splicing is very important. PILC cables are often designed with a jacket that acts as additional protection for the lead cover during the installation and operation of the cable. In most cases, the jacket is made of polyvinyl chloride or a PVC material. Another type of cable, three-conductor PILC cable, is designed a lot like a single-conductor cable. However, instead of the lead cover enclosing each cable of the three-conductor cable, it covers all three insulated conductors in one lead cover. In addition, over each cable's semiconductive insulation shield is a metallic shield. The shield is in the form of a copper or aluminum tape that is placed over the semiconductive shield on each of the three cables. The tape gives each conductor its own grounded metallic shield. Since a magnetic field occurs around an energized conductor, any electrical effect that insulated conductors have on one another can be contained within each single cable. When the three cables of a three-conductor cable are placed together, filler tapes and binder tapes are used. The filler tapes give the three conductors a round shape that keeps the lead from collapsing during installation and operation. In this case, a metallic binder tape is used to hold the three cables together. Up to this point, we've seen both single and three-conductor PILC cables and established that there are times when they will need to be spliced. Now let's look at some of the different types of splices that are commonly used in the T&D system. We'll begin with the most common type of splice in the system, a straight splice. A straight splice joins two ends of a cable that are the same type and design together. It is generally used to extend the length of an existing cable or to make cable repairs. Another splice that you'll see in a T&D system is a Y or branch splice. This splice is used to join three conductor ends of cable together at one location. As its name implies, a branch splice would be used where a feeder branches off in another direction from a splice to service more customers. A variation of a branch splice is a double branch splice. It's used, for example, when the feeder branches in four directions from one splice point, servicing customers on each side of the main feeder. As we mentioned earlier, the splices we've just seen join cables that are similar in design and makeup. An example of a splice that joins dissimilar cables is a trifurcating splice. A trifurcating splice joins a three-conductor cable with three single-conductor cables that have the same type of insulation. The design of a system will determine whether or not a trifurcating splice is necessary. For example, a trifurcating splice would be used when a system is not designed to permit the installation of a three-conductor termination on PILC cable. The last splice that we'll discuss is the transitional splice. This splice, as the name implies, makes a transition of a cable with two different types of cable insulation. The transitional splice we'll focus on joins a cable with paper insulation to a cable with a solid dielectric type insulation. Splices can be combined in many different ways. For example, a trifurcating transitional splice combines two types of splices that we've already seen, such as a three-conductor cable with three single-conductor cables. Each has a different type of insulation. Regardless of which way the splices are combined, the basic techniques to do the job are the same. With any splice, a detailed set of instructions should be followed carefully from the start and through to its completion. Well, we've looked at the different types of splices that are found when you work with PILC cables. We also saw an example of when each of these splices would be used in a T&D system. In the next part of the program, we'll learn how to prepare a PILC cable for splicing. In the last part of the program, we looked at different types of PILC cable splices. We saw how splices are designed to match different designs and needs of the underground T&D system. In this part of the program, we're going to look at how PILC, or paper lead cable, is prepared for splicing. The example we'll use is a straight splice on a 3-conductor paper lead cable. Before we begin the cable preparation, there are some important things to keep in mind when you make a splice. Regardless of the type of splice to be made, the original design characteristics of the cable must be fully restored. This is especially true when you're working with paper lead cable. The paper lead cable splice includes restoring the cable's paper insulation layer and those layers that assist the insulation in performing its job. Those layers include the insulation shield layers and the lead cover. As with any job, in order to protect yourself and your co-workers, safety comes first. Before you begin the splice, the work area must be made safe. That means if a splice is going to be made in an underground vault, the air quality must be checked to ensure it is safe before workmen enter the vault. Generally, for each cable splicing job, there is a specific set of instructions that should be followed carefully. Here's an example of a set of instructions for a splice. The measurements and dimensions for each layer in the preparation of the cable are included in the information. To prepare a cable for splicing, there are several tasks to complete. The first task includes gathering the tools that are necessary to do the job. Different types of cable, such as a paper lead cable and a solid dielectric cable, will require different types of tools. Let's take a look now at a variety of tools that are commonly used. This is a chipping knife, or a hack knife. It is used to remove the lead cover on the PILC cable. A shave hook is used to clean the cover when soldering is going to be done. A propane burner acts as a heat source to melt bar solder and to heat the flushing oil and insulating compound. Fire retardant cloths are used to handle and wipe the melted solder and to seal the ends of the splice. The solder is contained in melting pots, and a ladle is used to extract and apply the solder. In addition to the tools you've just seen, some of the more common tools needed to complete the splice include a knife, a file, a roll of tape for marking, and an assortment of hand tools. Most of the components needed to do the splice are included in a splice kit. The kit should always be checked before beginning to make sure that it is the right one for the job and to make sure all of the components are included. For example, some of the components of this kit include a splice sleeve, various types of oil-saturated tape, bar solder, flushing oil, and insulating compound. So once the tools and splice kit have been gathered at the splice location and the work area has been made safe, the job can begin. A workman places the cable ends in position and then cuts them so that they butt squarely together at the center line of the splice. Then the PVC jacket is taken off the required distance for each cable. A measurement is taken from the end of the cable so that the lead cover can be partially cut or scored, approximately 1/4 its thickness. The lead is scraped and cleaned beyond the scored area, and a styrene flux that comes with the splice kit is applied to the scraped area of each cable. This process will keep the lead from oxidizing and help the solder adhere to the lead cover a little later in the process. The lead sheath cover is removed from the end of each cable to the scored mark. In this case, a hack knife is used to cut the lead cover. The knife is tapped with a hammer. Always be careful not to damage or nick the cable layers below the lead cover. Once the cut has reached the scored mark, the lead is rolled off. As it's rolled off, it's important to check that the lead actually tears at the scored mark and bells out. Next, the cable binder and filler tapes are removed back to the lead, and they are cut off. The metallic shielding tapes are terminated at the required distance from the end of the cable. At this point, flux is applied to the ends of the metallic tape and then solder tack to secure them in place. Then the semiconductive insulation shield is removed, and the outer layer of paper insulation is removed back to the shielding tapes. This is to remove any residual semiconductive material on the outside layer of the insulation. A half layer of varnished polyester tape is applied over the paper insulation. The other workman is preparing the splice sleeve for installation on one of the cable ends. Each end is rasped, in this example for a distance of 3 inches. Then styrene flux is applied to the rasped areas. Now the sleeve is ready to be placed over one of the cable ends. It's important that the placement is done at this point, before joining the conductor ends with connectors. The propane burner is lit so that the process of heating the solder bars can begin. The solder needs to be hot enough to sweat or bond the connectors on the conductors. The cable insulation is ring cut at the specified distance. In order to avoid damaging the conductor, if it is not already round, the conductor should be rounded out before the insulation is removed. In this example, a utility splicing wrench is used. As the layers of paper insulation are taken off, they're counted. The total number of layers will be referred to later in the preparation process. Once the insulation and conductor shield are removed, the bare conductor is left exposed. Preparing to solder the connectors, a workman applies a layer of cotton tape or a fire-retardant material over the end of the paper insulation. This will protect the insulation from excess solder during the sweating of the connectors. A soldering paste or flux is applied to each of the conductors. The connectors are made of tinned copper and are cylindrical in shape. The connectors are spread and installed over the ends of the conductors on each cable. The connectors are then bent back down tightly over the conductor ends. The slotted area is left facing up on each cable. Next, the melted solder is tested to determine if it has reached the proper temperature. There are several methods of testing the solder. One method is to insert a piece of gummed paper into the hot solder. If the paper turns black or catches fire, the solder is ready. Another method of testing the solder temperature is to drop chips of styrene flux into the hot solder. If the flux ignites, the solder is hot enough. The ladles are also heated prior to contacting the hot solder. This is a safe practice, as a cold ladle can cause the solder to splatter. Always be very careful when you're working with hot solder. It can cause serious burns if it's mishandled. Now, using ladles to tin and sweat the connectors onto the conductors, the hot solder is poured into the slots and over the connectors. In this example, the workman uses his gloves to smooth the solder and smooth any sharp edges. The solid mass that forms at the end of the 2 cable conductors provides a very important electrical connection in the conductor splice. Next, the cotton or fire-retardant tape is removed from the connector area. To smooth down the connector, a file or non-conductive sandpaper is used on any edges that are sharp. Checking the smoothness of all the edges, this workman uses a mirror on all the hard-to-see areas. Then he wipes the exposed insulation with an approved solvent. The next process is called stepping the insulation. This process allows the insulation to be applied smoothly and with gradual thickness. To begin the stepping of the paper insulation, a cotton string or shoemaker's cord is tied at the correct distance from the edge of the paper insulation. 1/4 of the number of paper insulation layers that were counted earlier are now removed from the connector end up to the string. They're then torn off by pulling each individual layer against the string. Next, the string is tied onto the remaining paper layers at a distance closer to the end of the paper insulation. Once again, 1/4 of the layers of insulation are removed to the string. Finally, to complete the process of stepping the insulation, the string is installed at a distance closer to the edge of the insulation. Then another quarter of the layers are removed from the cable. In this part of the program, we've seen some of the tools used in cable splicing. We also learned the process involved in preparing a paper lead cable for splicing, and we installed the connector. In the next part of the program, we'll complete the splice. For now, answer the questions in your text. In the last part of our program, we saw a 3-conductor cable prepared for splicing. We also saw the conductors joined with solder connectors. In this part of the program, we'll rejoin the same crew as they complete the splice, restoring the cable's insulation and design characteristics. In addition, we'll see how the splice can be completely sealed by restoring the lead cover over the splice area. The workman will begin by applying new insulation over the spliced connectors. As with any splice, it's important to keep the application of the splice clean and free of contaminants. Before moving on, the insulating oil is poured into a kettle to heat. This oil will be used a little later in the splicing procedure. While the oil is being heated, the work on the splice continues. The diameter of the connector is measured using outside calipers. Using information from the splice instructions, the workman adds the thickness of the insulation buildup to the measurement on the outside calipers. Once insulating oil has reached the proper temperature, a catch pan is placed under the splice area, and the hot oil is poured over all the exposed paper insulation. It's very important to remember that the oil is very hot and can cause serious burns if not handled properly. The purpose of using the oil is to rid the insulation of any contaminants or moisture which have accumulated on it. This process is known as boiling out the insulation. Remember, once the oil has been used, it has been contaminated with foreign materials and cannot be reused. When the workman is satisfied that the contaminants have been boiled out, the process of re-insulating the splice can begin. Following the splice instructions, the first tape used is a 1/4-inch varnish polyester insulating tape. It is wrapped over the stepped area on one end and then half-lapped over the connector and over the stepped area of the other end. Then it is wrapped over the connector area until it is smooth and even. Next, 1-inch width varnish polyester tape is applied in half-lap layers over the connector. The tape is used until the insulation has built up over the connector to the proper thickness. To check the thickness, the calipers which we preset earlier are used. As the tape is applied, a slope buildup extends in each direction from the center of each connector. The tape is boiled out with a new batch of hot oil to make sure it is contaminant-free. Again, once the oil has been used, it should not be reused. Beginning with one end of the cable's metallic shield, the cable's insulation shielding is applied using a layer of tinned copper shielding braid. The shielding is then half-lapped over the taped insulation until it reaches the other cable shielding. This joins the individual cable's metallic shielding across the spliced area. The braid is now solder tacked to the cable's metallic shielding on each end to keep it from slipping on the insulation and to ensure electrical contact. This is repeated on all 3 cables. Then the cables are bound together using polyester tape. Starting 1 inch from the edge of the cable's lead cover at the end of the splice, all 3 cables are wrapped with shielding braid. The braid is half-lapped back over the lead cover. Finally, solder is used to tack the braid to each lead cover and to shielding tapes on the individual cables. This is done on both ends of the splice area. The braid is covered with 2 half-lap layers of 1 1/2 inch varnish polyester tape. The tape is applied across the splice, overlapping the lead cover of both cables. An opening is left at each end of the splice near the lead cover. This will allow insulating compound, which is used later in the splice, to enter and flow between the individual cables. Additional bar solder is added to the melting pot to be used later in the sealing process. In the last part of the program, before we installed the connectors, a lead sleeve was placed on one of the cables. The workman now centers the sleeve over the spliced area. Using a tinner's hammer or sleeve dresser, the ends of the sleeve are belled down by rotating or tapping the ends in a circular movement. This is done on both ends until the edge of the sleeve is in contact with the lead cover of the cable. Using the gummed paper tape supplied in the kit, the bell of the sleeve and the lead cover at each end of the splice sleeve are taped. This tape confines the solder as it's poured onto the splice sleeve. At this point, to avoid any pressure buildup, the sleeve is vented. There are several methods that can be used. In this example, a workman uses a plug cutter and cuts a small hole in the top of the sleeve. Next, a process known as wiping will be done on the ends of the sleeve to seal it. Once the solder has been heated to the proper temperature, the sealing or wiping can begin. Using a catch pan under the end of the splice sleeve, the solder is poured with the ladle over the end to be sealed. As it's poured and begins to tin to the sleeve and the lead cover, the workman uses a fire-retardant cloth to smooth or wipe the hot solder around the end of the sleeve. This is continued until the end is completely covered and smooth. To make an area smoother once the solder has cooled, a propane torch can be used to reheat approximately 1/3 of the wiped area at a time so that it can be re-wiped. The same process is repeated on the other end of the sleeve. The insulating compound is heated on the propane burner to fill the splice. At the same time, the gummed paper tape is removed. Now, following this company's procedures, before the splice can be filled with insulating compound, it needs to be pressure tested. A testing saddle with a gauge is placed over the vent hole. Pressure of 8 to 9 pounds is placed inside the splice. Then a soapy solution is applied over the wiped ends. If it holds the air pressure and there are no leaks detected, the seal is a success. If any air leaks are detected, the sleeve must be checked to find the problem, then resealed properly. With a successful seal, the splice is ready to be filled with insulating compound. To begin, a slot is cut into the splice sleeve at the opposite end of the vent hole. The heated insulating compound has formed a hot liquid that will generously fill the splice sleeve. Using a kettle, the melted compound is poured into the splice, through the slot, while displaced air escapes through the vent hole. The compound should be allowed to cool. During the cooling process, the compound may reduce in volume enough that more has to be added in order to completely fill the sleeve again. When the compound has cooled, the vent is closed with a metal plug, and the slot hole is bent closed. Then the area around the vent and slot hole are cleaned. Masking tape is installed around each, and the cleaned area is coated with styrene flux. To completely seal the sleeve, the holes are closed using melted solder and a soldering iron. Then the masking tape is removed. Next, the splice needs to be grounded and the jacket tape sealed. In this example, a number 2 AWG tinned bare copper wire is soldered to the center of the sleeve. The other end of the wire is left to connect to an established system ground, such as a ground bus in a manhole. To complete the splice, a layer of rubber tape that is covered with a layer of plastic tape is wrapped around the ends of the jacket to seal it from the environment. In this part of the program, we watched the completion of one type of 3-conductor straight paper lead splice. Although not all straight splices will be done exactly like the one we've just demonstrated, the splice you've just seen was designed to familiarize you with the general principles of splicing PILC cable. The process of wiping the sleeve is something that will become more familiar to you with time and experience. In the next part of the program, we'll watch as a workman demonstrates how to make one type of transitional splice. In the last part of the program, we saw the completion of a 3-conductor straight paper lead splice. At this point in the program, we're going to watch as a workman makes a transitional splice. In the example you're about to see, the 2 cables that will be spliced are single conductor cables. One is a paper insulated lead cover cable, and the other is an EPR or rubber insulation with exposed concentric neutral wires. Remember, there are a lot of different types of splices and sizes of cable. The type of transitional splice we'll be doing represents only one of those types. It is designed to familiarize you with the principles involved in making a transitional splice. Let's join the workmen now in the splice area. They've read the instructions, gathered the materials and tools, and made the work area safe. The workmen train the cables, then cut them so the ends butt squarely. Beginning with the solid dielectric cable, or in this case the rubber insulated cable, several turns of wire are wrapped around the cable at the specified distance. The concentric neutral wires are bent back away from the end and out of the way. Following the instructions, the semiconducting insulation shield is removed. If a knife is used, be sure not to nick or cut the insulation. Now, the entire area of insulation is sanded with a non-conductive sandpaper to remove any voids or residual semiconductive material. A cable cleaning solvent can also be used to wipe the area clean. The cable insulation is removed from the end of the cable for the required distance to install the connector. Once again, if a knife is used, be careful not to ring cut or nick the conductor. Next, a protective tape is installed over the conductor. The insulation is penciled or tapered and sanded till smooth. Then it's cleaned. Finally, the protective tape is removed. Next, preparing the paper insulated cable, the workman removes the PVC jacket a distance from the end of the cable. Being careful not to damage the lead cover, he begins by ring cutting at the mark and slitting the jacket to the end of the cable. Following the instructions for this splice and being careful not to damage the paper insulation, the lead cover is scored 8 inches from the end of the cable. The PVC jacket is buffed thoroughly the specified distance past the cutoff. This helps the tape stick to the jacket better later in the splice process. Then the lead cover is scraped clean beyond the scored mark. Next, the lead cover is cut and removed from the end of the cable to the scored mark. Then the insulation shield layer is removed back to the point where the lead cover has been taken off. And the outer layer of paper insulation is removed to the lead cover in order to remove any semiconductive material from the insulation. At this point, to protect against contamination, the exposed insulation that won't be removed is covered with 2 layers of varnish tape. The paper insulation is removed from the end of the cable to allow installation of the connector. Then, using tape to cover the conductor, the insulation is tapered 1 inch. The cables are now ready for the connector to be installed. An oil stop connector, which is a special type of compression connector, is used for this splice. This connector has a stop or dam in the center of the barrel. The stop helps keep the oil on the PILC insulation away from the solid dielectric insulated cable. Once the connector is in position, it's compressed. A recommended compression tool is used until the 2 prepared cables are joined with the required number of compressions. The connector is checked for any rough edges to make sure it is smooth and even. On this splice, semiconductive tape was rolled to fill in the indentations of the compression connector. Teflon tape is installed over the connector and paper insulation with a half-lap application. The tape is then applied over all of the paper insulation and over 1/2 inch of the lead cover. This layer of Teflon tape serves to keep the insulating oil on the paper insulation and not on the EPR insulation. Moving next to the edge of the Teflon tape in the center of the connector, additional semiconducting tape is applied. The tape is stretched to 1/2 its original thickness as it's applied. It's half-lapped in the direction of the solid dielectric cable until it overlaps the insulation. Then it is taken back over the connector until it overlaps the paper insulation. The next tape to be applied is 3/4 inch high-voltage rubber insulating tape. This tape is applied starting at the base of the pencil of the rubber insulation. The tape is stretched as it's applied to half its original width. Again, it's half-lapped back and forth across the connector area and penciled insulation area until it is built up to be the same diameter as the cable insulation. A wider 1.5 inch width high-voltage tape is used to add more insulation to the splice area. This tape is also stretched as it is applied. In this example, it begins 1/4 inch from the edge of the semiconductive insulation shield on the rubber insulated cable. The tape is half-lapped over the connector and the paper insulated cable to the edge of the lead cover. The high-voltage tape is applied back over the splice connector and back and forth until the diameter of the connector and the tape is at the desired thickness for this splice. The tape over the connector is applied so that it slopes down uniformly on each side of the connector. This distance is specified in the splice instructions. Next, 1/2 lapped layer of semiconductive tape is stretched over the applied insulation. The tape begins at 1/2 inch on the semiconductive shield insulation of the rubber insulated cable. It is then half-lapped over the insulation tape and over the lead cover on the paper insulated cable. The next layer of tape is friction tape, which is applied over the semiconductive tape. It overlaps the tape on both ends of the splice area and is half-lapped over the entire area of the splice. The metallic shield is applied over the splice area in the form of tinned copper shielding braid. The braid is started over the semiconductive insulation extending past the friction tape. Then it's half-lapped across the friction tape and over the lead cover of the PILC cable. Next, the shielding braid is solder tacked to the lead cover of the paper insulated cable. On this splice, rubber cement is applied over the shielding braid and over the entire splice area. On the paper insulated cable, the rubber cement is applied 1 inch from the edge of the outer jacket. The cement is allowed to become dry and tacky. Once it's dry, the outer jacket is built over the spliced area. Starting on the rubber insulated cable, it is taped with 2 half-lapped layers of rubber high-voltage tape. Then the rubber tape is covered with 2 layers of plastic tape. To ground this splice, the concentric neutral wires are bonded together. Then a number 2 bare copper wire is attached over the splice area. Styrene flux is applied to the end of the copper wire and lead cover. Then the end is soldered, permanently attaching it to the lead cover of the paper insulated cable. At this point, the concentric wires and the number 2 copper are bonded together. Then, to ground the splice, they are attached to the system ground. 2 additional layers of rubber high-voltage tape are then applied over the splice area. The entire taped area is covered with vinyl plastic tape to give the splice added sealing protection. We've just seen one way to make a transitional splice from a single conductor paper insulated cable to a single conductor cable with EPR insulation. In the next part of the program, we'll see how the cables are prepared for one type of trifurcating transitional splice. In the last part of the program, we saw the completion of a transitional splice. Earlier in this program, when we talked about other types of splices, such as a trifurcating splice, we said that it changes the design of the cable. For example, a trifurcating splice is a splice which involves changing a 3-conductor cable into 3 single-conductor cables. We also discussed how there are times when different combinations of splices are used in order to fit the different designs and needs of the T&D system. One of these combinations is a trifurcating transitional splice. In this splice, both the types of insulation and the design of the cable are changed. Paper-insulated cable is joined to a solid dielectric insulated cable, and a 3-conductor cable is joined to 3 single-conductor cables. In this part of the program, we'll see how the cables are prepared for one type of trifurcating transitional splice. The splice we'll be working on joins 3 single-conductor solid dielectric insulated cables to a 3-conductor paper-insulated lead-covered cable. This type of splice could be used when equipment won't accept paper-insulated lead cable terminations, such as equipment requiring elbow terminations. The trifurcating transitional splice that we'll be doing is a little different than the transitional splice that we saw in the last part of the program. This splice comes in a pre-assembled kit. The kit contains all the necessary components to splice with the exception of the connectors. This particular splice kit uses heat shrink tubes instead of tape. The tubes seal the oil on the PILC cable and perform the insulation and stress control requirements for an effective splice. As with any splice, the kit provides instructions that must be followed thoroughly. The tools for the splice in this example are basically the same as they are for splicing any paper-insulated cable. Once they've been gathered and the cable has been trained and cut, the job can begin. The jacket over the lead cover is removed the required distance by making a circular cut around the cable and down to the cable's end. The jacket is then removed from the cable end to the circular cut. Next, it is marked and scored at the distance that will be removed from the end of the cable. Again, a workman uses a hack knife to remove the lead to the end of the cable. The lead cover is removed from the cable by tearing the lead outward from the score on the lead cover. This process bells the lead cover away from the individual cables. Now, the end of the jacket on the lead cover is sanded to supply a better seal during the installation later in the process. The metallic binder tapes are removed along with the filler tapes by pulling them back to the lead cover and cutting them off. Next, the individual cable shields are taken back. In this case, the metallic shield is removed 6 inches from the lead cover. Then it's cut off, wrapped, and solder tacked on each individual cable. The semiconductive shield is removed to the edge of the metallic shield and cut off. And finally, the paper insulation is wiped with cable cleaner. The preparation of the cable continues with 2 measurements. The first is a measurement of half the length of the connector from the end of each cable where it's marked. Then, for this splice, a distance of 1.5 inches toward the lead cover from the first mark is measured and marked. At this point, a long strip of putty-like material from the kit called SRM, or stress relief mastic, is needed. This material serves 2 functions. The first is to supply electrical stress control for insulation. The second is to act as an oil block for the oil in the paper insulation. There is a backing on each side of the SRM strip. In order to make the installation easier, the backing on one side is removed, then rolled back so that the remaining backing is left facing the outside. Beginning at the mark closest to the end of the cable, 1/2 lapped layer of SRM is applied to each individual cable between the 2 marks. Next, the semi-transparent tube, also called the oil barrier tubing, is applied to each of the cable ends. The tubes are slipped over the cable ends to the edge of the lead cover. This tubing is made of a heat shrink material that works together with the SRM to keep the oil on the paper insulation. If the oil is not properly contained, the splice could deteriorate, causing premature failure. Once the oil barrier tubing is completely installed, the paper insulated cable will be transformed into a solid dielectric equivalent. With all three oil barrier tubes in the proper position, the heat shrinking can begin. An open flame torch is used in this example. The yellow portion of the flame is used. Beginning at the lead cover and using a brushing motion, a 3-inch section is shrunk completely and smoothed before moving on to the next section. Remember to keep the torch moving to avoid burning the tube until each section is completely smooth. Once the workman is sure that the entire tube area has been properly shrunk down, any excess oil barrier tubing is cut off, then cleaned with solvent. This is done to allow the installation of the next kit component, which is a conductive heat shrink tube. The tube serves the same purpose as the semiconductive insulation shield of a solid dielectric cable. Following the instructions, the black conductive tube is installed over the oil barrier tube at a specific distance from each cable end. Then, each is shrunk down, starting at the end which is closest to the cable end. The heat is applied using a brushing motion until the conductive tubes are completely wrinkle-free and smooth. The individual cable insulation metallic shields are connected or bonded to each lead cover. Tinned copper braid is wrapped around each metallic shield of the individual cable and the lead cover. It is then soldered to make a permanent contact point. An approved solvent is used to clean the lead cover and the oil barrier tube next to the lead cover. Insert pads made of SRM are used to block oil between the individual cables. After removing the protective paper from the pads, they are stuck together to form a T shape. Next, the pads are placed in the middle of the three individual cables with one leg of the T between all three cables. Any of the SRM pad that extends beyond the outside of the cable is cut and removed. A distance from the edge of the lead cover is marked. The lead cover is cleaned with solvent and sanded using a non-conductive sandpaper. Starting at the edge of the SRM pads, the rolled SRM is now half-lapped to the mark on the lead cover. The material will adhere to itself and to the lead cover. It is applied until its diameter is slightly larger than the lead cover. The next kit component to be installed is a conductive breakout tube. The purpose of the tube is to electrically connect the conductive shields of the individual cables to the lead cover. It also helps the PILC cable retain internal oil pressure. Be certain not to confuse this tube with any other. It is usually clearly marked conductive. The breakout tube is installed over the individual cables until it contacts the SRM insert pads, then overlaps the black conductive tubes of the cables by 1 inch. To shrink down the breakout tube, heat is applied to the main body just below the individual cable openings. The heat is then extended over the lead cover. Once this is complete, the tubes over the individual cables are shrunk down, beginning at the center and moving outward. Each cable end can now be prepared for the connector installation. The oil barrier tubing, SRM, and the paper insulation are squarely removed for the installation of the connector. Always use extreme care when removing these layers to avoid damaging the conductor. Because heat shrink tubes were used, penciling or stepping the paper insulation is not necessary. SRM material is installed at the edge of the semiconductive tube to make a smooth transition for the heat shrink tube. The preparation of the PILC cable is now complete. Next, the workman prepares the solid dielectric cable. Following the instructions, he cleans the end of the cables of any contaminants using a rag and solvent. The jacket is removed the required distance. The copper tape shield is then removed. Then, the semiconductive insulation is carefully removed the proper distance. Being careful not to ring cut or nick the conductor, the insulation and conductor shield at the end of the cable are removed. At this point, the process of preparing the solid dielectric cables is complete. When all three of the insulation ends have been removed, the remaining insulation is sanded with non-conductive sandpaper and cleaned with cable cleaner. Then, small strips of SRM material are wrapped around each cable at the edge of the semiconductive insulation shield. This is to help reduce electrical stress and provide a smooth transition for the heat shrink tubes that will be installed later. In the next part of the program, we'll see the cable ends joined with a connector and spliced using a heat shrink splice. For now, answer the questions in your text. At this point in the program, two types of cable have been prepared for a trifurcating transitional splice. They include a 3-conductor PILC cable and 3 jacketed solid dielectric insulated cables. In this part of the program, the workman will finish the splice. Remember, this is an example of only one type of trifurcating transitional splice. It uses heat shrink tubes to rebuild the layers of cable. Make sure that you're familiar with the types of splices your company uses. When we completed the last part of the program, a workman had wrapped small strips of SRM material around each cable at the edge of the semiconductive insulation shield. Let's pick up where we left off and begin by putting an insulating sealing breakout tube over the end of the solid dielectric cable ends. The individual cable sections are placed on the cable first, away from the cable ends. Be sure to note the difference between this insulating sealing breakout tube and the conductive tube used in the last part of the program. Mistaking the tubes could cause the splice to fail. Next, a telescoping set of heat shrink tubes is placed with one tube over each of the solid dielectric cables. Each tube will serve the splice differently. Taking a closer look, the smallest tube is the stress control tube. It helps the splice by reducing the amount of electrical stress to a safe operating level. On other types of splices, this tube performs the function of a stress cone. The red insulating tube supplies part of the insulation for a splice with material having a high dielectric strength. Next is the insulation and shielding tube. It supplies both the remaining insulation and a layer of insulation shielding. The outside layer is a black semiconductive layer. The last, and also the largest tube, is the black reinforcing tube. It goes over the connector area and provides added strength to maintain the internal oil pressure of the PILC cable. At this point, the cable ends are brought together and the connectors are installed. In this splice, a solder connector is used. The connectors are installed similarly to the solder connectors we saw earlier. Next, the connectors are sanded to make sure there are no rough edges. Then they are wiped clean with an approved solvent and a rag. The rolled SRM is used again, this time on the connector. Here it is half lapped over the connector on one cable to cover the connector and to fill in any gaps. These gaps may exist between the connector and the insulation of the cables on each side. On this splice, the diameter of the connector is built up until it matches the diameter of the cable's insulation. One layer of the SRM should overlap the solid dielectric cable and the PILC cable insulation by 3/4 of an inch. The SRM is applied smoothly without any gaps until the diameter of the connector is the same as the cable insulation. Now, the smallest stress control tube is centered over the connector. The connector overlaps each cable's insulation shield. All 3 cables are prepared following the same process. The heat shrinking of the tubes begins using the heating procedure we followed earlier in the splice. The stress control tubes are heated starting at the center of the tubes. This allows the air to exit the tube in each direction as it's shrunk down. The tubes have been completely shrunk down when an outline of the SRM material can be seen over the connector. To completely shrink the ends, the torch is pointed directly at the ends of the tubes. Using a brushing motion avoids scorching the tubes or cables. Now, returning to the center, the other end of the tube is shrunk down to the end. The tube is checked for flat or bumpy spots, or areas where the tube does not conform to the outline of underlying cable. If any problems are found, the tube must be reheated and the area shrunk down completely. Next, each of the 3 insulating tubes are centered over the stress control tubes. Insulating tubes are shrunk over the stress control tubes, beginning in the center and moving to each end. A constant brushing motion is made until both ends of the insulating tube are completely shrunk down on all 3 cables. Then the next tube in the splice is installed. The insulating and shielding tube is centered over the red insulating tube on each cable. Although this tube is thicker than the 2 previous ones and will take longer to shrink down, the installation and shrinkage are done exactly the same as they were on the previous tubes. When all 3 of the insulating and shielding tubes have been installed, the reinforcing tubes are slid over them. Then, with the reinforcing tubes in the proper position, they are each shrunk down. The shrinking of the reinforcing tubes completes the installation of the oil stop system, stress control, and the insulation and shielding components for the individual cables of the splice. Next, we'll see how to install the metallic shielding, make the electrical connection of the metallic shield, and re-jacket the spliced area. Since both cables of this splice are jacketed, we'll be following specific instructions for this type of cable. Beginning on this splice, 3 lengths of ground braid are solder tacked to the metallic shield of the solid dielectric cable. Then, each braid is taken across the spliced area of each cable and soldered to the lead cover of the PILC cable. On this splice, an external ground is needed, so an additional length of ground braid is used. The end of the ground braid is attached to the lead cover. A piece of ground braid is wrapped around all of the soldered braided ends. Then each end is soldered to ensure its electrical connection. Now the braid is bent up to clear the lead cable. Then a layer of sealing mastic is applied around the cable at the edge of the jacket. The braid is laid across the mastic and pressed into the mastic. Then more mastic is wrapped over it. Once the splice is complete, it will be environmentally sealed with an external ground. In this example, starting with the metallic shields of the solid dielectric cable, tinned copper mesh is half-lapped around all 3 individual cables. It wraps around the ground braids and overlaps the lead cover of the PILC cable. Then it's soldered to the lead cover and the ground braids. The sealing breakout, which was installed on the cable, is slid down toward the splice. This leaves the individual slots on the end completely over the cable jackets. Next, the breakout is shrunk down starting on the area over the mesh and moving to the individual cable tubes. When a red adhesive bead appears at the end of the tube on the cables, the tubes have been completely shrunk down. A half-lapped layer of 1.5-inch polyester tape is installed over the tinned copper mesh. This is to protect the tinned copper mesh during the remaining installation of the splice. The tape should not extend to any areas beyond the mesh. To complete the splice, an outer jacket will be installed to seal and protect the splice from the environment. This heat shrink sleeve is called a re-jacketing sleeve. It has a heat-melting adhesive on the inside. The sleeve itself is held together with a metal channel. To install the jacket, the workman peels off the inner liner of the sleeve. Then the sleeve is wrapped around and finally centered on the splice area. There are 2 rails on the sleeve that are brought together. The metal channel is installed sliding from one end of the rails in order to hold the sleeve together. In this example, because more than one piece of channel is used, a channel clip is slid onto the channel's ends to make sure the entire railed sleeve is held together. If any excess channel extends over the edge of the sleeve, the channel should be broken off. The sleeve is now ready for shrinking. Beginning at the center of the sleeve, the workman uses the same method of shrinking that he used for all the other heat shrink tubes. As the heat is brushed over the jacket, it shrinks quickly. Like the sealing breakout, the re-jacketing sleeve will begin to show adhesive when it is completely shrunk down. Looking at the rejacketing tube, we can see how it overlaps the sealing breakout tube on the solid dielectric cable and on the jacket of the PILC cable. This overlapping completely encloses the splice and the exposed cable. Because the sealed jacket is similar to the rest of the cable, the splice is protected from the environment. We've just completed one type of trifurcating transitional splice. However, this company's specifications also require external grounding of the splice. So the grounding braid that was left exposed would now be connected to the system ground at the splice location. In addition, if any cable tags were required, according to company specifications, they would be installed at this time. And finally, before putting the cable back into service, the splice is allowed to cool, and then, according to your company's policy, the splice is electrically tested. Well, we've covered a lot of information about cable splicing, and although the program has focused mainly on specific processes, it's also covered some more general splicing information. We watched as a crew installed a splice on paper-insulated cables, and again when they spliced a PILC cable to a solid dielectric cable. In addition, we went through some of the basic procedures to follow and tools to use when making any type of splice. Remember, with any splicing job, in order to make it safe and successful, always follow the instructions you've been given from start to finish.